Next thing to talk about with respect to floods is something called recurrence interval. This is something that you're all familiar with. Recurrence interval is essentially the number of years, the length of time that we'd expect on average to occur before floods of the same magnitude. So if you have a recurrence interval of 10 years, you'd expect that flood to occur on average, once every 10 years, that sort of thing. Of course, that's not the way nature works perfectly. Lots of things can change. And it's also a probability. So you can have a 10-year flood in 3 consecutive years. It's unlikely, but you could conceivably do it. A recurrence interval of something like, let's say, a 100-year flood, again, we would expect to occur one time per 100 years, right? So 1x, that's supposed to be 1x, one time per 100 years. So that would be one event per 100 years. So if you do the math, that's 0.1 or 1%. So there's a 1% chance in any given year that you're going to have a 100-year flood. So if you had a 100-sided die and you rolled it, you could imagine that out of those 100 sides on the die, one of them says flood and 99 of them say no flood. Well, if you roll that die 3 times, there's a possibility, it's very small, that it would come up on flood each time, right? So you could have a 100-year flood without doing anything else to the climate or the landscape or anything. It's statistically possible, although unlikely, that you could have a 100-year flood 3 years in a row. But how do we know whether something is a 100-year flood or a 500-year flood or whatever? Well, we do that by calculating these recurrence intervals, and we do it based on observational data, observations, and statistics. And basically, the way you do it is you would take, let's just sort of imagine a series of observations here. Let's say that somebody founded a town in a part of the country where nobody had been before. And I don't know, we'll make it out west someplace. We'll make it 1880. And they lived there for a few years, 1882, 1883, and 1884. So that's, what is that? That's 5 years total. 1, 2, 3, 4, 5. 5 years of records. And they had, let's say, 1 flood a year, and they measured the discharge of those floods every year. They were very forward-thinking people in the 1880s. And so this is discharge in cubic feet per second. And the discharges were, let's say, 2,000 CFS in 1880, 1,550 in 1881, then 1,750, 2,250, and 1,650. All right, so how do you take that information and extrapolate, interpolate, and make some guesstimations as to what floods are going to be like over the next 50 years or 100 years that you're going to be there, right? In general, we have relatively short observational records, particularly if you're not on the East Coast. So what do you do? Well, the first thing you do is, with these data, is you calculate the rank. And the rank simply means that you rank these in order of largest to smallest. So the largest of these floods was the 1883 flood. The second was the 1880, then 1882, 1884, and 1881. And then you're going to calculate the recurrence interval based on these data. So the recurrence interval is calculated as n plus 1 over m, where n, in this case, is 5. It's the number of years of record. So we have 5 years of record. That goes in for n. And m is the rank, the relative magnitude, okay? So we would have 6 divided by the rank here. So let's see if we can do these pretty quickly. So The recurrence interval would be 6 divided by 2 for the 1880. That would be 3. Let's skip down. 6 divided by 3 in 1882 would be 2. 6 divided by 1 would be 6. 6 divided by 4 would be 1.5. 6 divided by 5 would be 1.2. Okay. All right, so now we've got these recurrence intervals, and what have we just calculated? We've calculated that we would expect to have a flood of this magnitude, 2,250 CFS, once every 6 years. Why? Because we have 5 years here and it happened once. So the next time it should happen, according to this, is year 6. And so forth. So anyway, right off the bat, your mind might be swimming a little bit and seeing all the problems inherent in this kind of calculation. It gets worse. So now what we're going to do is we're going to plot these data with discharge over here on a regular scale. Regular scale, what does that mean? Regular scale means this is going to go from 0 to 500 to 1,000 to 1,500 to 2,000 to 2,500. Every tick mark represents an increase in Q, I shouldn't have done that like that, Q, of 500 cubic feet per second, right? Make sense? Get this up here now. But we're going to calculate the recurrence interval, or plot the recurrence interval on the x-axis using something called a log scale. Log scales are a little bit funny. I'm going to post something to Moodle that shows you how this works. But basically, each big tick mark, as you go across here, is not going up by, say, 500 each time. It's going up by a factor of 10. So if this was 0.1, this would be 1, this would be 10, this would be 100, and this would be 1,000. And they're evenly spaced apart. And inside these will be subticks, which get closer and closer and closer to each other. So this would be 0.2, 0.3, 0.4, 5, 6, 7, until you get to 1. And then this would be 2, 3, 4, 5, 6, 7, 8, 9, 10. And this would be 20, 30, 40, 50, 60, 70, 80, 90, and 200, and so forth. Okay, anyway, the long and the short of it is we plot these data, recurrence interval versus discharge, on this graph. With recurrence interval on the logarithmic scale on the x-axis and discharge on a normal scale on the y-axis. And so let's just plot these. Recurrence interval of 3 would be somewhere here with a discharge of 2,000. That would be here, 2,003. 1.2 would be 1,550, so 1.2 would be somewhere in here, 1,550, something like that. Recurrence interval of 2 and 1,750 would be here maybe. Recurrence interval of 6 and 2,250 would be, I don't know, up here. And 1.5 and 1,650 would be, I don't know, somewhere like that. So we have 5 data points. They all will kind of fall in a line. It won't be perfect. There'll be some noise, some scatter. And then what you're going to do, or what we do mathematically, is we draw a line through those data, best fit line. And you can do this mathematically in Excel. I'll talk about how to do it. But for now, we're just going to kind of eyeball it. And you actually do a surprisingly good job if you eyeball it. So you put a straight line as best you can through those data. It'll look something like that. And what you have now is based on 5 discrete data points, you have some ability now to calculate recurrence intervals of very, very large floods and smaller floods. Now, of course, the smaller floods are going to be more common, so those aren't the ones you have to worry about. But look at this. We can say, even with 5 years of data, we can now go out to a 100-year flood, which would be here, 100-year recurrence interval, and calculate what its discharge would be. So based on this, it looks like it would be about 3,500 or so CFS. So a flood of a certain magnitude, 3,500 CFS, should occur once every 100 years, based on these data. And then remember, with a rating curve, which is something we talked about in another lecture, a rating curve, you can link discharge to stage. So you can actually know how high the water would be for a given volumetric flow. So now we would know, okay, how much of the town would be flooded, for example, or much of somebody's fields would be flooded in a 100-year flood. We'd be able to see how high the water level goes. Obviously, there are lots of problems with that, and let's just think about what some of those might be. What would be some of the problems associated with this approach? Problems with this statistical rating curve calculation. All right, so what are some of the problems? Well, actually, what I'm going to do is give you guys a second to think about it and just brainstorm to yourselves a couple of the issues that we might expect to have that would impact our ability to accurately calculate recurrence intervals. I'll just sit here silently for a second while you do that. I'm sitting here silently because I don't know how to hit pause. All right, got some ideas? What are some ideas? What are some reasons why this rating curve that we calculated from the 1880s might not apply today? Well, let's see. What are some problems? Well, one, of course, is that the climate might be changing from the 1880s to today. Certainly it's changing as we move further into the future. We're putting all these greenhouse gases in the air. The air is getting warmer, and warm air holds more moisture. So if you have more moisture in the air, you have more moisture that can come down in rain events. And so we would expect, and we're already beginning to see, heavy rains are becoming more common on a global scale. What else? That would certainly change flooding. Another possibility is urbanization. Something we talked about in an earlier video. If we take trees and we cut forests and we turn them into farmers' fields, or we take grasslands or fields and we turn them into parking lots, we very much change the nature of flooding in the watershed. And it's not just entirely solely due to parking lots and everything. In farmers' fields, farmers, particularly in Iowa and places like that, put in these things called tiles. I don't know if you've ever seen these. Tiles are long pipes with perforations in them, and they get buried underneath the ground. And so the idea is that when you have, say, in the spring, when you got all this soggy ground from the snow and the moisture and everything's been frozen, you want the field to dry out as fast as possible so that you can get out there and till it and fertilize it and get it planted. So they bury these pipes, so the water, instead of staying in the ground and sort of being waterlogged, makes its way down slowly, finds its way into these pipes. The pipes are at an angle, and the water just runs right out. So it's like sticking a straw into the bottom of a Coke and sucking it out, right? You just start pulling that water out of the fields, and so the fields dry up quicker. Well, that certainly has positive benefits for farmers in the spring, but it also means that when you have a big, heavy rain event in the middle of the summer or whenever, the water, instead of being soaking into the ground and staying there sort of like a sponge, it moves down into these pipes, into these tiles, gets funneled to neighboring streams and enhances problems with flooding. So we have climate change, we have urbanization. What about with the stream itself? What about with the stream itself? Well, of course, we have things like channelization. Rivers are being straightened in order to reduce flooding. Well, that works if you're in the area that was straightened, but what if you're downstream? If you're in an area, here that's pretty flood prone, this is a flood prone area, right? You straighten out the channel, the water gets out of the system faster, and maybe this area sees fewer floods. But now you're flushing water even faster down into this lower part of the river, and so the flood risk is going to increase. So anyway, these are all issues that we have to think about when it comes to looking and thinking about flooding. So we'll stop there. If I can figure out how to do it. And I can't. Hold on. I'm looking. There it is.